Let's look at what actually happens when objects are copied. Whenever you assign one object to another, or pass an object by value to a function, or return an object from the function, a copy of that object is created. But how this copy happens? Who decides what gets copied and how deeply it should be copied? That's the job of a copy constructor. Let's see an example to see how exactly it works. Here we create S2 from S1. The copy constructor is automatically called. It creates a new object with the same values as the original. If we didn't define our own copy constructor, then the compiler would generate a default shallow copy. The compiler created copy constructor works fine in general. We need to define our own copy constructor only if an object has pointers or any runtime allocation of the resource file, like file handle or a network connection maybe. The default copy constructor provided by the compiler performs only shallow copy. That means it simply copies the value of data members, including pointers, without creating a new memory. So this is important. It doesn't create a new memory for them. As a result, both the objects end up pointing to the same memory location, which can lead to unexpected changes or even runtime errors when one object modifies or frees that memory. So to avoid this problem, we use a user-defined copy constructor. That is, we define our own copy constructor and we do not rely then on default shallow copy constructor provided by the compiler. In a user-defined copy constructor, we make sure that any pointers or references in the copied object point to newly allocated memory. So this process is basically called deep copy. It ensures that each object has its own independent copy of the data. In short, the default copy constructor performs a shallow copy and user-defined copy constructor enables deep copy that keeps the object safely independent. So the copy constructor is called when a new object is created as a copy of the existing object. In other words, it is used during object initialization. On the other hand, that equal sign assignment operator is called when already existing object is assigned the value of another existing object. So remember, copy constructor creates a new object from the existing one, while the assignment operator that we will discuss later on updates an already created object with the values of another. So they both look similar in code, but they occur at different stages of the object's lifetime. Now let's go through an example of a class with statically defined non-dynamic attributes, which helps you to understand how copying works safely when no dynamic memory is involved. So in this example, we have a class named distance, which contains two member variables, feet and inches. Both of these are statically defined attributes, meaning they are stored directly inside each object, not through pointers or dynamically allocated memory. So the class provides a default constructor that initializes both members to 0, and then a parameterized constructor that allows us to set custom values. Now in main function, when we create two objects d1 and d2, where d2 is initialized as a copy of d1. So when this happens, the default copy constructor generated by the compiler is called automatically. So what it do is it performs member-wise copy, meaning that each data member of d1 is copied directly to d2. Since feet and inches are simple data types, they are of integer and double type, so this shallow member-wise copy works perfectly fine. So there is no shared memory, no dynamic allocation and no danger of double deletion. When we call show function for both objects, you will notice that even though the values are the same, the memory addresses of feet and inches are different for each other. That's because each object has its own independent copies of static attributes stored on the stack. So this example clearly shows that when a class only contains non-dynamic members, the default copy constructor and assignment operator generated by the compiler are completely safe to use. You only need to define the custom or user-defined copy constructor when your class contains pointers or some dynamically allocated memory. So in this example, we are using the same class name distance, but this time instead of storing the values of feet and inches directly, we store pointers to them. This means feet and inches are dynamic attributes. They do not hold the actual data, but the memory addresses that pointed somewhere else. In the constructor, these pointers are assigned to external variables. Now look at what happens in main. We define two separate variables f and I and pass their addresses to the constructor of d1. Then we create another object d2 as a copy of d1. When that happens, the default copy constructor simply performs a shallow copy, meaning the memory addresses stored inside d1's pointers are copied directly to d2. So now both d1 and d2 contains pointers to the same external variables, that is the same memory locations for f and I. When we call show function, you can see that while the addresses of a pointer variable themselves are different for each object, the values stored inside those pointers, that is the actual addresses they point to, are identical. This means both the objects are referring to the same data in the memory. That might seem harmless at first, but it can lead to a serious problem. For example, especially if one of the object modifies or deletes the data, leaving the other with a dangling pointer. This is the classical example of why shallow copying fails when classes use pointers or dynamic memory. So to fix this, we need to implement a user-defined copy constructor that performs a deep copy, allocating new memory and copying the actual values so each object manages its own separate data safely. In short, static attributes are safe, the default copy works fine, but dynamic or pointer attributes require a custom deep copy to prevent shared memory issues. Let's talk about an important detail in C++, why the copy constructor uses constant reference as in its argument and why we generally pass arguments by reference or by pointer. So let's see this step by step. Part 1, why the copy constructor uses constant reference. So the copy constructor has this syntax. You can see, you might wonder why not just pass the object by value. Well, if we try to pass it by value, that would require meaning a copy of an object to pass into the constructor. By making that copy, would call again the copy constructor, which would then try to make another copy, then another, and so on, leading to infinite recursion and a compiler error. That's why copy constructor takes its arguments as by reference, so it can refer directly to the existing object without triggering another copy operation. Now let's see why the constant keyword. Because we do not want to accidentally modify the source object that we are copying from. So together, constant reference means referring to the existing object and do not change it. So constant reference means refer to the existing object and do not change it. So this makes the copy constructor both safe and efficient. Now let's extend this idea. In general, when we pass by value, by reference or by pointer, depending on what we need, pass by value means you use it for small simple data types like integer, character, double, so the function gets its own copy of the data. In pass by reference, you use it when you want to avoid copying large objects or when the function needs to modify the original variable directly. Similar to reference, pass by pointer gives the flexibility to handle the null pointer and dynamically allocated data. So in constructors, especially the copy constructor, we pass by reference because we need to access an already existing object and we do not want to create another copy of it. So using constant reference ensures that a constructor only reads from the original while saving constructing a new object based on it.